If cross-entropy feels like a weird number you just hope goes down, let's make it intuitive. You have models that output numbers. You want a single, sensible score that tells you how wrong they are and how to fix them. By the end of this video, you will be able to compute that score by hand for a tiny example. See why negative log likelihood matches cross-entropy and build a small NumPy baseline to monitor training. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple, concepts-first Python that helps you solve bigger real-world problems. Think about a simple classifier that guesses which of two labels is true. You care not just about the final label, but how confident the model was. Cross-entropy and negative log likelihood are the quick, principled answers people use because they punish confident mistakes much more than timid ones. That makes them ideal for probabilistic classifiers and neural nets where probabilities are central. Intuitively, cross-entropy measures how surprised the model is by the truth. If the model put most probability on the right label, surprise is low. If it put mass on the wrong label, surprise is high. A helpful concrete image is a game of 20 questions. Each question halves the remaining possibilities, costing 1 bit. Negative log likelihood, measured in bits, tells you how many perfect 20 questions this prediction is worth. We will build up from one prediction to a full batch baseline. First, we will compute the surprise for a single example. Then we will see how that equals cross-entropy for a one-hot target. After that, we compare two predictions, then convert raw scores into probabilities with temperature, and finally compute a mean batch loss with NumPy. This stepwise approach keeps the math grounded in intuition. Now we compute negative log likelihood for one label. This snippet computes the negative log likelihood for one label. The list P holds predicted probabilities for two classes, and the variable Y is the correct class index. The value NLL equals minus log base 2 of the correct class probability, measuring how surprised the model is in bits. Lower values mean the model assigned higher probability to the truth. 0 happens only for probability 1. We print NLL in bits so you can intuitively compare it to questions asked by a perfect 20 questions player. The printed number shows how many bits of surprise this prediction carries. Next, we rewrite the same idea using a one-hot target distribution. This snippet rewrites NLL as cross-entropy with a one-hot label. The list YVEC represents the target distribution, placing all mass on the true class. The expression CE computes minus the sum of YVEC times the logarithm of P, which reduces to minus log of the true class probability. The check C equal uses the language math is close to confirm it matches the earlier NLL value exactly for one-hot targets. This demonstrates why cross-entropy collapses to negative log likelihood for classification. The printed Boolean confirms the two formulations agree. Now let us compare two different model outputs for the same example. This snippet compares two predictions by negative log likelihood and selects the better one. The new list Q is a second model's probabilities for the same example. We compute NLLP and NLLQ using the same minus log base 2 of their true class probabilities. The model with a lower NLL assigns more probability to the correct label and is preferred. This simple compare clarifies that pushing probability mass onto the true class is exactly what NLL rewards. The printed tag shows which prediction wins. Next, we turn raw scores into probabilities using temperature to show how confidence changes loss. This snippet uses NumPy to turn logits into probabilities with temperature. The array Z holds raw scores, also called logits, and NumPy exp combined with division by tau creates a softmax distribution PZ. A smaller tau sharpens the distribution, making the top class more confident. A larger tau softens it. We then compute temp loss as the negative log of the true class probability from PZ. If you decrease tau, confidence rises and loss typically drops. Increasing tau does the opposite. The printed loss shows how a sharper softmax can reduce NLL. Finally, we aggregate into a tiny batch and compute the average cross-entropy. This snippet builds a tiny NumPy baseline, batch cross-entropy. The matrix Z contains logits for 3 examples, and YB are their integer labels. We compute P with a row-wise softmax via NumPy exp and a row sum. Then index the correct class probabilities using P at row indices and label indices. Taking negative logs gives per example losses, and their mean is the batch loss you would optimize. As predictions concentrate on the correct classes, the average loss goes down. The printed value is a simple, interpretable baseline for monitoring training. Mapping this toy example to a real project is straightforward. Replace the tiny logits matrix with your model outputs and compute the same per example loss and mean. Use the batch loss to drive gradient steps and log the average loss across epochs to see training progress. Recap. What it is: cross-entropy is the average number of bits of surprise the model assigns to true labels. When to use it: for probabilistic classification where you want to reward putting mass on the correct class. One caveat: it punishes confident wrong predictions heavily, so poorly calibrated models can look worse even if accuracy is similar. Next step: tune the softmax temperature on a validation set to control confidence, or vary batch size to stabilize the mean loss while you train. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.